Your kids could get free or low-cost health coverage from Medicaid or CHIP. Even if you've applied before, they may be eligible now. Kids up to age 19 are covered for checkups, vaccines, dentist visits, hospital care, and more. And if they already have Medicaid or CHIP, remember to renew every year. Visit insurekidsnow.gov or call 877-KIDS-NOW. Paid for by the U.S. Department of Health and Human Services.
Lowe's knows how to help make your home holiday ready for less. Get Select Style Selections vinyl flooring for just $1.99 per square foot and have it installed before the festivities begin. Our team can help you every step of the way. See a Lowe's Red Vest associate or visit Lowes.com/holiday install to get started. Lowe's, we help, you save. Basic install only. Date restrictions apply. Subject to availability. Installed by independent contractors. See associate for details. Contiguous U.S. only.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome, curious minds. Today, we're looking at something pretty radical, overturning a decades-old idea about Mars. Forget the notion of just a fully liquid, maybe dying heart beneath that dusty red surface. New seismic data, this is from NASA's InSight mission, it reveals Mars holds a secret, a solid core. And it's shockingly similar to Earth's, which is, well, it's a discovery that completely rewrites the history, the really violent history, of the red planet and its lost oceans.
Yeah, what's truly remarkable here is how our understanding of Mars just keeps evolving. It's constantly pushing the boundaries of what we thought was possible, It forces us to reevaluate these long-held assumptions we've had. We know Mars today is, well, a cold, dry, seemingly desolate world, like a frozen desert, basically. Yet the evidence that's been building up, it strongly suggests a very different past, one that held this compelling promise of, well, abundant liquid water, and perhaps, maybe even the potential for life.
Right.
And the key to unlocking this huge mystery, it turns out, lies hundreds of kilometers down, way beneath its now dusky, arid surface.
Yeah, for years, Mars has felt like this colossal planet-sized cold case, hasn't it? How did it go from being potentially watery, maybe even vibrant, to the parched desert it is today? It's a question that's really driven decades of exploration.
Absolutely.
And today, let's call them our forensic team, the scientists working with the InSight mission, they finally cracked a really crucial piece of that puzzle. It's dramatically reshaping our understanding of Mars's interior. We're talking incredible new insights from seismic studies. They literally offer us a peek into its innermost secrets, like a planetary autopsy report almost.
And this raises a really important question for all of us, I think. What can the very core of a planet actually tell us about its entire history, its trajectory, its ultimate fate? We'll be looking at how these recent observations have not just refined, but really significantly deepened our models, suggesting that Mars might be far more like Earth deep down than we previously believed. And this is more than just geology, It's a profound story. Planetary evolution, the delicate balance of magnetic fields, and the incredibly specific conditions that are required for a world to remain hospitable, to hold on to its life-giving potential over, well, cosmic timescales.
So our mission today, as we dive into this, is really to uncover the secrets of Mars's core, understand why its structure and its history matters so much to the planet's past and maybe its future, and also to see how science, like a persistent detective, painstakingly builds knowledge, step by careful step. So prepare to have your assumptions about the red planet challenged.
We'll trace this fascinating journey of scientific discovery, right from the initial hypotheses, which were often based on remote observations, looking from orbit, to the latest and most precise seismic measurements from InSight. And we'll try to connect these seemingly abstract, kind of complex details to the grand sweeping narrative of Mars's really dramatic transformation. It really is a planetary detective story.
Okay, so let's start with the Mars we think we know, the one we see today. When we look up at the night sky, see that unmistakable red dot, or when we see those amazing images beamed back by the rovers, what comes to mind? I mean, it's a vast, chilly desert, right? That's the image most of us have.
Precisely. Yeah, you've captured it perfectly. The Mars we observe today is characterized by an extremely thin atmosphere. Really thin. It's mostly carbon dioxide, something like 95%. And this thin envelope, it offers very little protection from solar radiation.
Okay.
The surface pressure is less than 1% of Earth's at sea level. Just incredibly low.
Wow, less than 1%.
Yeah. And temperatures, well, they rarely, if ever, get above freezing, often plunging way down to minus 60 degrees Celsius or even colder at the poles, and the almost complete lack of significant stable liquid water on the surface. That's one of its most defining features right now. It is, by all accounts, a very harsh place. Inhospitable, a true frozen desert.
And you think about those pictures, those iconic images from the rovers, Spirit, Opportunity, Curiosity, Perseverance. You see those dusty, rust-colored plains stretching out forever, barren, rocky landscapes, those clear, often kind of salmon pink skies, sometimes with those swirling dust devils. It's got this immense geological beauty for sure. Like, absolutely not a place you'd picture taking a swim, right? Or finding a river, or seeing oceans. It feels like a world stripped bare of the very things that make Earth so, well, alive. But that's not the complete picture, is it? Not by a long shot. That stark reality of Mars today actually makes the evidence for past water even more compelling, doesn't it? It really underlines the sheer scale of the change the planet went through. There's a huge amount of compelling, really undeniable evidence telling a very different story about Mars's past, a time when it was a very different kind of world.
Indeed. Yeah, what's truly remarkable is the overwhelming geological evidence, meticulously gathered over decades by orbiters and rovers like Curiosity and Perseverance. This evidence suggests that liquid water once flowed freely, abundantly even, and perhaps for long periods across the Martian surface. We're talking about conditions that were, well, incredibly far more hospitable than anything we see today. A Mars that would be honestly unrecognizable to us. Maybe resembling a young Earth.
A young Earth. Wow. So what kind of evidence are we talking about specifically?
Well, it comes in many forms, and each one is like a powerful clue, really undeniable. For instance, we found numerous dry lake beds. These are expansive basins that clearly once held standing water. You can see ancient shorelines, delta structures, sedimentary fans.
Like river deltas.
Exactly. Yeah, consider Jezero Crater, where Perseverance is right now. The images show these intricate river deltas, very much like, say, the Mississippi Delta here on Earth. This is where a river once flowed into a vast lake, depositing sediments over potentially millions of years. And within those ancient sediments, scientists have found specific minerals. Things like clays and sulfates, phyllosilicates like smectite, chlorite, or evaporites like gypsum, jarosite. These are minerals that could only have formed if liquid water was present for a long time. They're not subtle hints. They're definitive chemical signatures, like a chemical fingerprint of past water, locked away for billions of years.
Okay, so dry lakes, specific minerals. What else?
Well, beyond that, we see these dramatic valley networks etched into the landscape. They're not just random cracks, they are intricate branching systems, really similar in their shape, their morphology, to river systems on Earth. Think of those dendritic patterns you see in aerial photos of the Amazon basin, for example.
Right, like tree branches spreading out.
Precisely. And these aren't just small channels. They're often kilometers wide, hundreds of meters deep. They're unmistakable evidence carved by the relentless flow of ancient rivers, long-lived rivers, not just, flash floods. And then there are the sedimentary layers. You can see them in canyon walls, like in Valles Marineris, or exposed in crater rims. These finely stratified deposits, laid down layer upon layer over vast time scales. They are textbook examples of deposition in standing bodies of water, just like sediments settle in lakes or seas here on Earth. It indicates a long, sustained period of water activity. All of this, taken together, paints this vivid, irrefutable picture of a world that was once rich in water.
So, yeah, this overwhelming evidence, it really begs the question, doesn't it? How could a planet, now so incredibly arid, so seemingly lifeless, have once supported such an abundance of liquid water? What allowed for that much thicker atmosphere and a milder climate? The conditions that were clearly needed for surface water to exist? It's just such a radical transformation, a monumental shift. What drove such a huge change?
Okay, to really get a handle on Mars's incredible transformation from potentially watery to the cold, dry world we see, we need to understand something absolutely vital about our own planet first. Earth, its internal engine, its heart, you could say. All right, so if we're trying to figure out Mars's big shift, we really need to start with Earth, don't we? I mean, why is our internal engine so incredibly good at protecting our atmosphere and, keeping life going?
Yeah, if we connect this to the bigger picture, the whole idea of planetary habitability, a key property of Earth's remarkable ability to sustain life, comes directly from its core. Our planet has what we call a differentiated core. There's a solid inner core, mostly iron and nickel, and that's surrounded by a churning, swirling liquid outer core. also mainly iron and nickel, but mixed with some lighter elements like sulfur and oxygen. It's this dynamic internal structure that's absolutely critical for generating Earth's global magnetic field.
Okay, solid inner, liquid outer.
Right. And this specific arrangement is what drives the geodynamo.
You won't see the engineer that slams the Nissan Rogue's door 13,920 times. Or the corrosive chamber that simulates 15 years of life in 5 months. Or the Rogue heat-baked for over 300 combined hours. What you will see is a vehicle that can take punch after punch and keep rolling. Nissan, #1 in new vehicle quality among mainstream brands by J.D. Power. We put it through the worst, so you get its best. For J.D. Power 2025 U.S. Initial Quality Study Award information, visit jdpower.com/awards. Awards based on 2025 model year. Newer models may be shown.
Effect. Essentially, you have convexing currents within that liquid outer layer. Think of it like boiling water, but with molten metal. These currents are driven by heat escaping from the solid inner core as it cools and crystallizes, and also by the planet's rotation. The Coriolis effect stirs things up. And this whole process generates a powerful, expansive magnetic field.
Right.
This field stretches way out into space, forming this invisible protective bubble around our entire planet. We call it the magnetosphere. It's a truly amazing, self-sustaining system.
So it's like an invisible shield. That's a good way to think about it. Constantly deflecting all this harmful stuff from the sun, charged particles.
Exactly. It deflects harmful, charged particles that are constantly blasted out by the sun, especially during solar flares and coronal mass ejections. These solar winds, as they're called, are incredibly energetic streams of protons and electrons. And without that magnetospheric shield, they would just relentlessly strip away our atmosphere over geological time.
Like a sandblaster.
Yeah, that's a good analogy. Much like a powerful sandblaster eroding rock, it's this continuous, silent battle happening way above our heads. The magnetosphere acts like a bouncer, basically, redirecting these high-energy particles around Earth. Without this magnetic protection, our atmosphere, and along with it the conditions for life, would slowly but surely vanish. It's also why we get the auroras, the northern and southern lights. That's some of those deflected particles interacting with our atmosphere near the poles, a beautiful side effect of our planet's shield.
Okay, that makes sense. So with that essential understanding of Earth's shield in mind, what about Mars? Does it have a similar life-preserving magnetic field today? Because, I mean, if it doesn't, that immediately points to a very different situation, doesn't it? Maybe one of vulnerability, of loss.
Right. Currently, no, it doesn't. Mars utterly lacks a global magnetic field today, certainly nothing like Earth's. This is a critical difference and a major reason why Mars is the cold, dry world we see now. However, and this is a really crucial piece of the puzzle, the evidence points to a very different past for Mars, too. From residual magnetization found embedded in the Martian crust. Essentially, you have rocks on the surface that still hold a fossil magnetic signature. This signature dates back to when they first formed and cooled down billions of years ago in the presence of an active magnetic field. Scientists are quite confident that Mars did once possess such a global field.
So it had a shield, too, early on.
It seems so. Orbiting spacecraft like Mars Global Surveyor actually mapped these magnetic anomalies in the crust. They confirmed that an ancient dynamo was active, likely for maybe the first billion years or so of Mars's history. And this ancient field was probably generated by a core structure similar to Earth's, meaning it likely had a solid inner core and a liquid outer core capable of driving that dynamo.
Okay, so it had one but lost it. What are the implications of that loss?
They're profound. Truly profound. It marks a pivotal moment in Mars's story. Scientists generally hypothesize that the eventual loss of this magnetic field was a critical turning point, perhaps the critical turning point. Without that protective shield, the relentless solar wind would have had direct, unimpeded access to Mars's ancient, much thicker atmosphere.
Right, no more bouncer.
Exactly. Over millions, hundreds of millions of years, this energetic bombardment would have stripped that atmosphere away, particle by particle. Through processes like sputtering, where particles get knocked off, and ion pickup, where atmospheric gases get carried away by the solar wind. Think of it like a constant slow leak into space. This atmospheric loss, in turn, would have led directly to the rapid and irreversible loss of surface liquid water. As the atmospheric pressure dropped, water just couldn't stay liquid on the surface anymore. It would either freeze, or sublimate, turn directly into gas and escape into space, or maybe retreat underground. It's this cascading chain of events, starting deep inside the planet with the dying dynamo, that ultimately led to the barren landscape we see today.
Wow. So it all comes back to the core. This really raises that central question then. What exactly happened to Mars's internal engine? What switched off that planetary dynamo? What turned Mars from potentially vibrant and watery into the desert it is now? That's the core mystery, isn't it? And to answer that, we couldn't just look at the surface anymore. We had to go deeper, which is precisely why missions like InSight were conceived, right?
Precisely, yeah. While missions like NASA's amazing rover Spirit, Opportunity, Curiosity, Perseverance have been fantastic surface geologists, analyzing rocks and soil. And orbiters like ESA's ExoMars Trace gas orbiter study the water cycle, and NASA's Maven N look specifically at atmospheric loss. A fundamentally different kind of mission was needed to probe that core question, the question about the planet's deep interior. We needed to listen, not just look.
And that mission was NASA's InSight lander. It touched down, quite incredibly, back in November 2018. Landed in a region called Elysium Planitia, chosen because it's relatively flat, geologically quiet, which is ideal for its sensitive instruments. Its primary goal, really groundbreaking, was to study seismic activity Marsquakes, as we call them. The aim was to reveal, for the very first time, the planet's internal structure, its crust, its mantle, and crucially, its core. InSight listened patiently to Mars for 4 years, making its last contact in December 2022. Sadly, its solar panels got too dusty to keep it powered, but it's data that continues to revolutionize our understanding. It's this treasure trove scientists are still digging through. Okay, so here's where it gets really interesting. In 2021, there was this seminal paper, a truly landmark study that came out of the InSight mission, led by Simon Staler and his colleagues. This paper gave us the very first direct look, the first robust measurement of Mars' core. So after all that anticipation, all that listening, what did they actually find? What was the initial verdict on Mars' depth secret?
Well, using that invaluable data from the Marsquakes, those faint rumbles and tremors deep inside the planet, Staler's team analyzed how the seismic waves traveled through Mars. Think of it like shouting into a canyon and timing the echoes. Different materials inside the planet reflect and transmit seismic waves differently.
Okay.
So by precisely timing how these Marsquake echoes, specifically the P waves, which are compressional waves, and S waves, the shear waves traveled from the quake's origin, through the crust, the mantle, down into the core, maybe reflecting off internal boundaries, and then finally traveling back up to InSight's super-sensitive seismometer called SACE. They could literally map the internal layers, like a planetary sonogram. It was the first time we ever directly heard Mars's internal structure.
Incredible. So what did that first map show? What did the core look like in that 2021 study?
Right. So their in-depth analysis, based on about a dozen of the larger Marsquakes they'd recorded by then, revealed a few key things. And some were a bit surprising at the time. They modeled a core with just a single liquid layer, basically a big molten ball of metal. And this core was surprisingly large. They estimated its radius at about 1,800 kilometers, which is roughly half of Mars's total radius. Quite big for a planet Mars size.
Half the radius, wow.
Yeah, and furthermore, it turned out to be less dense than you'd expect for a purely iron-nickel core, like Earth's is mostly. This density deficit, which they inferred from how fast the seismic waves traveled through it, strongly suggested it was rich in lighter elements, things like sulfur, oxygen, carbon, maybe hydrogen, mixed in with the iron and nickel.
And why is that important, the lighter elements?
Well, those lighter elements significantly affect the core's melting temperature if they lower it. That makes it much more likely for the core to stay liquid for longer, rather than solidifying quickly as the planet cools down over billions of years. So this was a crucial insight. It potentially explained how Mars might have kept a liquid core and maybe a dynamo going for some time, even though it's smaller than Earth.
Okay, so large, liquid, less dense, full of lighter elements. Did they say anything about a solid inner core like Earth's?
That's a really crucial detail from Staler's paper, and it shows how careful science is. They did not explicitly rule out the possibility of a solid inner core. The authors themselves meticulously stated in the paper that the signal strength from the data they had at that time and the specific types of seismic waves they could confidently analyze were simply not robust enough, not clear enough. They couldn't definitively identify the faint signals you'd expect from seismic waves crossing an inner core boundary. So it was an excellent first measurement, truly a monumental achievement, but they explicitly acknowledged its limitations and left room for further discoveries. It set the stage, waiting for more data or better techniques to perhaps see deeper.
Right. And science is truly a journey, isn't it? Not just one destination. So while Staler's work was absolutely monumental, a groundbreaking first look, the story of Mars' core, as you said, didn't stop there. Just recently, new, even more refined results came out. This was from Huixing Bi and colleagues, published in the journal Nature, and this took our understanding to a whole new level, didn't it? What did they uncover that was so significant, building on that initial foundation laid by Staler's team?
Yeah, this is a fantastic example of scientific progress in action. You see one study building directly on the previous one.
You won't see the engineer that slams the Nissan Rogue's door 13,920 times, or the corrosive chamber that simulates 15 years of life in 5 months, or the Rogue heat-baked for over 300 combined hours. What you will see is a vehicle that can take punch after punch and keep rolling. Nissan, #1 in new vehicle quality among mainstream brands by J.D. Power. We put it through the worst, so you get its best. For J.D. Power 2025 U.S. Initial Quality Study Award information, visit jdpower.com/awards. Awards based on 2025 model year. Newer models may be shown.
And also the power of persistent, clever data analysis. This latest study by Beal and colleagues, they leveraged additional insight data collected over a longer period after Staler's first analysis. So that meant a larger catalog of Mars quakes to work with, including some that were perhaps deeper or more energetic, sending clearer signals through the core.
Okay, more data.
More data, yes. But crucially, they also employed some novel and highly sophisticated data analysis techniques, new ways of processing the signals. By carefully selecting specific types of seismic events, ones that happen at just the right distances from InSight, to maximize the chance of detecting faint reflections from deep within, and then expertly extracting an incredibly weak signal from what was often quite a lot of instrument noise. They managed something remarkable. It was like seismological detective work, filtering out all the background chatter to finally hear the planet's deepest whispers clearly.
And what did those whispers tell them? What was the key finding?
Their key finding was unambiguous. They identified the clear presence of a solid layer within the liquid Martian core. This wasn't just a subtle hint. It was the distinct, solid inner core. And they even estimated its radius at approximately 610 kilometers.
610 kilometers? How does that compare to the overall core size?
Well, if the total core radius is around 1,800 kilometers, then 610 kilometers is a substantial fraction. About a third of the radius, or roughly 15% of Mars's total radius, is this solid inner core. This is a profound revision to our understanding. It shifts our model of Mars's interior from that simple, fully liquid core picture to a more complex, differentiated one, much more like Earth's structure.
Okay, wow. So we thought it was just liquid, and now we find this distinct solid part inside. That feels like a really big shift. What does this solid inner core actually mean for understanding Mars's history? And crucially, for that long-lost magnetic field we talked about. Why is this particular detail, solid inside liquid, such a big deal? How does it connect to a planet's life support system?
Well, what's truly profound here is the implication this discovery carries. It's huge. The very presence of a solid inner core tells us definitively that crystallization is happening. Solidification is taking place as the planet cools over geological time. This process, where liquid metal slowly solidifies at the center, and in doing so releases latent heat and lighter elements. This process is absolutely critical for a planet like Earth to generate and sustain its magnetic field for billions of years. It's essentially the engine that drives the planetary dynamo.
Ah, okay. So the solidifying process itself is the key.
Yes, exactly. To elaborate a bit on its significance, a core structure with both a solid inner part and a liquid outer layer is fundamentally much more like Earth's setup. On Earth, it's precisely the temperature differences and the chemical changes happening at that boundary between the solid inner core and the swirling liquid outer core, plus the heat flowing out into the surrounding mantle that drive the vigorous convection currents in that liquid outer layer. As the core cools, iron crystallizes onto the inner core. This process releases lighter, more buoyant elements into the liquid outer core, and these lighter fluids then rise, creating convection, like a lava lamp effect, but with molten metal. These convection currents, this organized movement of molten, electrically conducting metal, coupled with the planet's spin, are the engine for the dynamo that generates a planetary magnetic field. Therefore, this new discovery of a solid inner core on Mars makes it significantly more likely, much more plausible, that a robust dynamo, capable of producing a protective magnetic field, was indeed active on Mars early in its history. And perhaps it was sustained for a significant period. It provides that missing ingredient, that Earth-like structure needed for a strong, long-lasting dynamo.
And for you, listening right now, this gives us a much clearer, much more scientifically solid pathway for Mars to have once had the conditions needed for a thicker atmosphere. And as a result, that abundant flowing liquid water on its surface that the geology points to, it connects the deep, hidden, internal processes of the planet directly to the surface conditions we were talking about earlier. It closes a major loop in our understanding of how Mars could have been so different back then.
Okay, so when we hear about one study, like Staler's in 2021, initially suggesting a fully liquid core, and then another one, like Bin's just recently, reporting a solid inner core, it might, at first glance sound like a scientific argument, maybe even a controversy or contradiction. But that's absolutely not what's happening here, is it? This is actually a really wonderful illustration of how science actually works. It's self-correcting progressive nature.
Absolutely not a controversy, no. Not in the sense of a fight. It's actually an excellent and incredibly common example of the iterative nature of science, how data collection and analysis evolve. Staler's initial findings in 2021 were, without question, groundbreaking, a huge first step. They provided the first solid constraints on Mars's core size and state, a monumental achievement, giving us that first internal glimpse. But as they themselves very carefully noted in their paper, the data they had available at that specific time and the methods they used just didn't have the necessary signal strength or clarity. They couldn't definitively confirm or deny the existence of a solid inner core. They were very clear about that limitation, which is just part of good scientific practice.
Right, they pointed out what they couldn't see yet.
Exactly. So it's not about one being right and the other wrong. Staler's 2021 work was the best possible model based on the data and techniques available then. The new study by Bi and colleagues, well, they benefited from more data. Newer data accumulated as InSight kept listening, recording more Marsquakes, maybe some deeper or stronger ones. And crucially, they applied more refined, novel data analysis techniques. They basically found clever ways to pull out those weaker, more subtle seismic signals. Signals that were previously either buried in the noise or just beyond the detection capability of the earlier methods. It's this continuous process. Initial models, based on the best evidence at the time, get tested, refined, expanded upon as new information comes in, and as the analytical tools themselves get better. This is precisely how scientific understanding deepens. It becomes more precise over time, with each new study building carefully on the last one.
It's a fantastic example of the scientific method in action, isn't it? Not like a sudden eureka moment, but this persistent, incremental buildup of knowledge. And you see this iterative process even within related research groups. You mentioned even Staler's initial model was revised slightly in 2023.
That's right, by Henri Hamuel from Université Paris-Cité and his colleagues. Their updates help to further reconcile InSight's seismic findings with other existing evidence about Mars's core size and density. Often these refinements incorporate other types of geophysical data too, constraints from Mars's gravity field measurements, or its rotation, things learned from orbiters. This ongoing dialogue, this constant refinement of models and theories as new data comes in, is absolutely central to how science progresses. It's really collaborative, not confrontational, a shared journey towards getting a clearer picture.
Okay, so this isn't the final word, the absolute end of the story about Mars's core, but it's a major new chapter, a really significant one. What does this new discovery, this confirmation of a solid inner core, mean for the scientific community moving forward? What can we expect next in Martian science now this piece is in place?
Oh, this result is absolutely going to have a significant and I think very exciting impact within the planetary science community. We can definitely expect more reanalyses of the entire InSight data set. That's almost guaranteed. Scientists will be scrutinizing these new methods used by Bi's and colleagues, looking for independent confirmation. They'll likely apply these techniques to other seismic events, maybe look at different types of seismic waves to see if they can consistently detect that solid inner core signal and maybe refine its properties even further. The goal is always to solidify a finding like this through multiple lines of evidence, multiple analyses.
Makes sense. Check the work, basically.
Exactly. Check the work, try different approaches. And beyond just the seismology, there will be thorough discussion about the broader geological and geophysical context. Researchers will be looking in detail at how this new model of Mars's interior solid inner core, liquid outer core, fits with everything else we know. That includes geochemical models of Mars's bulk composition, the precise gravity field data from orbiters that tells us about mass distribution inside the planet, and those previous studies of the crustal magnetic anomalies. This collaborative, cross-disciplinary process is how we strengthen our collective understanding of planetary evolution. It ensures the model makes sense in the big picture. It's honestly a very exciting time for Martian seismology and planetary science. It's prompting new theoretical models and definitely fueling further investigations into the red planet's deep past and maybe even its future evolution.
So let's pull back for the big picture then, the grand narrative of planetary science. Why is understanding the inside of Mars, this newly revealed internal structure, why is it so critical, not just for Mars itself, but for our fundamental understanding of planets in general, both here in our solar system and maybe even worlds beyond?
Yeah, this really raises an important question that goes way beyond just Mars. Understanding the interior structure of any planet in our solar system is absolutely critical. It's fundamental if we want to develop robust, accurate theories about how these celestial bodies form in the first place, how they grow, and, crucially, how they evolve over billions of years. The core, really, is the engine of planetary change. It influences everything from the geology on the surface to whether a planet can hold onto its atmosphere. Consider this. Before InSight's work, and especially before this latest discovery, confirming the solid inner core, models for Mars that suggested an internal structure very similar to Earth specifically, that differentiated core with both liquid and solid parts, capable of powering a long-lived dynamo, well, they weren't generally favored. Many models lean towards Mars having cooled faster, maybe having a fully liquid core, or perhaps one with a different composition that just couldn't support a dynamo for as long as Earth's has run.
So this discovery really changes that baseline assumption.
It shifts the perspective dramatically, yes. This confirmation of a solid inner core means Mars's early history might have been much more Earth-like deep down than we generally thought possible. And this knowledge helps us tackle these really fundamental, profound questions, like, how big does a rocky planet need to be to generate and sustain a protective magnetic field over billions of years? What are the key ingredients, the compositional factors, the thermal conditions required for a planet to maintain a habitable climate, an environment where liquid water can persist over those vast stretches of geological time? It pushes us to rethink the minimum requirements, maybe, for forming an Earth-like planetary system.
And for you, listening right now, this knowledge, it stretches far beyond just our red neighbor, doesn't it? It directly feeds into our ongoing, very ambitious search for habitable exoplanets, those worlds orbiting distant stars. As we find more and more exoplanets, this detailed case study of Mars gives us crucial reference points. What to look for, perhaps. It helps us better understand the precious rarity of Earth conditions, especially that long-lived, active geodynamo providing our essential shield. It really highlights what a truly unique and, you could say, fortunate world our home planet is, still protected by its powerful internal engine humming along after 4.5 billion years. So we're left with a much richer picture now, a far more dramatic and ultimately a more nuanced story of Mars. It wasn't always just the cold, barren desert we see today, completely lacking that global magnetic protection. It seems it had a fighting chance, didn't it? An internal engine that was once very much alive and kicking.
Precisely. We now have much stronger, more direct seismic evidence supporting a past Mars that was a truly dynamic world. A world with an Earth-like core generating a powerful magnetic field, which in turn likely sustained a thicker atmosphere and allowed for, very probably, abundant flowing liquid water on its surface. Its transformation into the cold, dry desert planet we know today wasn't instantaneous, but it was this gradual yet profound planetary drama. A saga driven directly from its very core outwards, as that internal engine eventually cooled, slowed down, and the dynamo died. It serves as this really powerful illustration, how the internal processes of a planet, those hidden mechanics deep beneath the surface, ultimately dictate the surface environment, and by extension, its potential for supporting life. Mars, in many ways, is a cautionary tale. It's a natural laboratory showing us what can happen when a planet loses those vital internal protections. Hashtag outro.
Wow. What an incredible journey we've taken today. Venturing from the dusty, familiar surface of Mars right down into its newly revealed core, a solid inner core, surprisingly Earth-like. We've seen how this patiently gathered seismic data, collected over years by InSight, combined with ingenious, refined analysis, can unravel mysteries millions and millions of miles away. It's just a testament, isn't it, to the power of scientific exploration and that relentless human drive to understand our universe, one planet, one core at a time. It's almost poetic, really, that after all these years of just gazing at Mars, sending rovers to, taste soil, we're finally getting to listen to its heartbeat.
Yeah, this ongoing exploration of Mars' interior really reminds us that the planets in our solar system aren't just static objects hanging in space. They are dynamic worlds. They have complex, often dramatic histories. They're constantly evolving, constantly transforming over cosmic timescales. The InSight mission, even though it's now silent on the Martian plains, it continues to speak volumes through its invaluable data. It's pushing us ever closer to understanding the dramatic saga of the Red Planet and, really by extension, our own place within the cosmos. It truly reshapes our understanding of how planets like ours evolve.
So as we wrap up this exploration, Maybe consider this, Mars' story, its journey from a potentially vibrant, watery world shielded by a magnetic field, much like early Earth perhaps, to the dry, barren desert it is today. It's a stark reminder, isn't it, of how fragile planetary habitability can actually be. It's this delicate balance of internal processes, external forces, a kind of cosmic dance that can turn a world from blue and wet to red and dry over billions of years.
And maybe ask yourself, what if, lurking deep within other seemingly barren worlds we observe out there, there are similar clues? Clues to past lives, past habitability, or maybe even the subtle potential for future transformations we haven't considered. Mars really asks us, how truly unique is Earth's fate? And what other profound planetary secrets are just waiting to be revealed? Hidden beneath the surfaces of other worlds, just waiting for us to listen patiently to their whispers across the silence of space.